Thank you for inviting me. Yeah, so today I'm going to talk about a line of work that we started several years back, and hopefully I'll get to a paper that we published in the last 2 years, some more recent research. And the area is about, related also to what Craig talked about how do we model and try to understand some incentive issues within the context of recommender systems when trying to incorporate the fact that users have preferences and they have prior biases, and that might not be the same as what the recommender system preferences are, or the goal of the recommender system. Of course, it's going to be a stylized model that tries to capture some of of these types of dynamics. So it won't be like a solution that you can really take to Word and implement it, but it's going to be giving some design insights of what types of mechanism design ideas you can deploy, and we're going to be looking in particular to mechanism design sort of approaches without the use of money, because in recommender systems it will be weird to say that we're going to start paying people to also to take up on action. So we're going to be thinking about the mechanism design through information asymmetry. So what is the goal? Say in a recommender system is recommend the option that is of highest value to the user. But what does what is the value of every option for the user? So for that you actually need to gather information to decide that. But that information is actually also gathered by the users themselves. So prior users will give you information about the different options, and that information is going to help you decide which option is better for the next users. So users in recommendation systems are both producers and consumers of information. And for overall welfare optimization in a recommender system, you need to balance exploration and exploitation in the same way that we try to balance exploration and exploitation in the context of a bandit algorithm. Right? So we need to incentivize users to explore many options that are on the table so that we can gather information about alternatives and decide which one is the best option. But we also want to exploit so that we recommend to the users what we currently believe are the highest reward options from what we already know. The problem when you start incorporating user preferences and prior biases is that prior biases tend to lead to lack of exploration. So, for instance, you think about the context of the restaurant business. People might have some prior biases that tell them that the reward from this well-known restaurant is higher than the reward from this other restaurant, and so most probably everybody will go there. The feedback that you're going to get is going to reinforce that belief, and you're never going to explore this new incumbent, for example, in the market. But as a recommender system, you really want to incentivize people to go to that option that you have less information about. So you need to incentivize people to explore these more noisy, for instance, options or options that a priori seem inferior. So how can we do? So the purpose of this talk is how can we do that through information asymmetry that exists between the users and the recommender system. So what the types of things that we're going to capture in our model is that we're going to have repeated interactions between a planner and multiple agents. Each agent is going to pick one among a set of available options. For example, it could be restaurants, it could be routes in a network, or hotels. Agents will arrive, they will pick an action and report feedback to the planner about the reward of the action that they chose. And they are strategic. So their goal is to maximize reward conditional on the information that they have, which is their prior signals, their prior bias, and the recommendation or whatever signal the recommendation system gives to them. Right? And the planner wants to learn the best alternative and maximize overall welfare. And the important part here is that the agents, when they report feedback feedback privately to the recommender system. Right? So the recommender system is also sort of like controls the flow of information, right? So, this is the tool that the planner can use to design mechanisms that are incentive compatible that will incentivize exploration. The fact that we can control the flow of information that's coming from the agents and what we reveal to the new agents that are incoming. So the question we're going to ask is, can the planner induce exploration when they control this information flow and learn the best alternative, and at what rates? So can we, for instance, achieve the rate of learning that we would have achieved, or at least in the same order of magnitude, if there were no preferences, if the users were just taking the actions that we recommended? So if this was just a normal bandit problem, you'd have some rates of learning. Can we get the same rates of learning? And then I'll focus on these three questions in the first part of the talk and give you some key ideas and techniques that we developed on how you can achieve this. And then in the end, I'm going to also talk a bit about some extensions, and in particular, what happens when there is unobserved user heterogeneity. So users' preferences are governed by private types which are not revealed to the planner, and those private types can lead to biased estimates if you don't incorporate them into your estimation process. Right.
Just a real quick clarification. So for recommenders, there are like two notions of exploration often, and I think I see what one you're getting at. But sometimes, hey, we want to explore to understand a user's specific preferences, or induce a user to explore. And the other is we want to induce behavior, for instance, on the part of users that help us learn more in a way that can be generalized.
The second, yeah.
The second. It is the second.
Yeah, yeah.
Okay.
So in fact, like the stylized part of this model is going to be that agents arrive once and leave, right? Or you could also think of it as agents being myopic. They only think about the one interaction at a time. So you really want to learn for other users, or learn for the same user who just didn't think about this long-term effect. So let's look at the main model, which we term Bayesian incentive-compatible bandit exploration. So you have a planner. You have T users that arrive sequentially. Each can take one of K actions. Each action has a mean reward, mu I, which is in 0, 1. And there is a common prior belief on each of those mean rewards. So every agent has some, the agents have some prior beliefs about these rewards. So these prior beliefs also, we need to impose some assumptions that they have some sort of overlap, those prior beliefs. So like this is my prior on what is the mean reward for arm K. This is my prior on what is the mean reward for arm I, and so on and so forth. When someone takes an action, you have some realized reward Ri, which is stochastic IAD with mean mu I. And at each time step, the planner recommends an action, IT, so the interaction between the planner and the users. I'm going to send them a recommendation. Here's the action that you should take. And the users, take some action. Ideally, it should be the action that was recommended, and report that realized feedback to the planner.
Distribution on the prior it's not necessarily the same as the distribution on the realized reward.
Yeah, no, this is a hierarchy. So you have like some distribution of realized rewards with some mean mu I,
yeah.
And then you put a prior on what does that mean, right? So agents
Prior on the mean.
have a prior on that mean of the distribution. Right.
Oh, okay. But they know what the variance is.
Sure, but the risk sort of like neutral, so they just care about the mean.
Okay.
So when they think about which action I should take, I just think about what is the mean given the current signal. So in the beginning, I'll think that it's just mu1 0, mu I 0, and so I'll just pick the one with the prior. Yeah.
Just to understand, the user reports the realized reward for having followed the recommendation or for any decision you've taken?
So they will report the realized reward for the decision that they took, and we observe also the decision that they took. For now, I haven't incorporated incentives at all. So in this slide, I assume that they actually follow the recommendation, and we'll see what our recommendation is to satisfy so that they follow the recommendation, right?
And do you assume that they report their actual reward?
Yes. There's trust in that process. So far, without any further constraints on how our recommendations should look like, it's just we care about, for instance, also the regret. So this is like if we knew the actual realized means of the actual true means of the arms, this is the best that we could hope for, and this is the reward that we get from the recommendation algorithm, which could be randomized. So that's the standard regret. Or you could also be looking at Bayesian regret, where those means are also, where this regret is calculated in expectation over the common prior, which is a slightly weaker performance measure. Right, and our goal is to get vanishing regret, or that like this thing grows sublinearly with t, ideally we want the ex post regret because it is sort of prior free, but this is also a measure that we'll analyze in this work, and it's slightly easier also to achieve, but we also have algorithms for the ex post regret.
Are the priors updated and everyone, it remains a common prior and it's updated as they observe the rewards?
Yes, but like each agent comes once, they only observe once. So the only update that happens is through my recommendation.
Right.
So
for future ones, so initially it's not.
Everybody has nothing. Everybody has their prior. They come to the system. They receive the recommendation. That's the only extra signal they have, right? And so they update their beliefs based on that signal only, right?
But it's a common prior. Everybody has the same belief.
In the beginning, right? Everybody has the same. Afterwards, different people receive different signals, right? So you receive the first recommendation, nobody else saw, right? So the second, so on and so forth. So the only
they deviate. Their beliefs deviate depending on
they deviate after they see the recommendation, right? So you might think, you're the first person, you're going to receive an uninformative signal. I'm just going to go with the prior. So the second person now comes. I have information from the first person. I'm going to send them a signal. Maybe that changes their belief.
But when they come in with the same belief that the person at the first time came in.
So here's a common prior, and then I'm going to talk about in the second part when you have heterogeneity in the prior, and when that heterogeneity also correlates with rewards, and what can we do? In this type of work, we also did when you have heterogeneity based on observable characteristics. So if they come with a context, and then you could have a common prior given the context, and you could do contextual bandits. But that extension is more straightforward than what I hope to get to. So far, the setting is equivalent to just a stochastic multi-arm bandit problem. It's a very well-studied problem. You can get root T regret. And the interesting things happen when you start thinking about incentives. So the recommendation algorithm cannot be any bandit algorithm. It has to be an algorithm such that given the recommendation, so if I'm recommended to play action I, my expected mean reward, right, given that information, that extra signal, right, should be bigger than playing any other action given that recommendation, right? So this is a complicated posterior sort of update that has to do with me, I'm announcing how the algorithm works. So as a planner, I announce how the algorithm works. And now when you see recommendation, you actually, this is it's a complicated, a signal that comes through how the algorithm works, what what you might have observed by other people. So I'm not going to go into how do you exactly do this posterior update, but we'll assume that people, perform this update exactly. And our goal is to design bandit algorithms that satisfy this incentive compatibility constraint.
So can you say that again? So I'm still not clear on what user number 100 sees.
Just the recommendation.
Just the recommendation.
Just the recommendation.
What do they know about?
They know the algorithm the recommendation algorithm that I follow.
Oh, so that is.
Yeah. Public knowledge. Like I announce that this is how my recommendation system works.
Okay.
Right.
But there also has to be a little bit of trust on the part of the users that they believe that this recommendation was generated by that algorithm.
Yes, exactly. So it's a commitment. Yeah, it's like a commitment power.
Because otherwise, what you recommend to all these other users, it can have zero influence on the 100 users.
Sure.
But the planner is learning As a
The
part
planner is learning. It receives information learning. They have commitment device on the algorithm, commitment power on the algorithm. Think about it as, like you might interact with the system many times. If I didn't satisfy this, you were going to statistically, detect it or something. So that's one way that could have commitment power.
And then does the 100th user know that they are the 100th user, or they don't know their?
Yes.
They know that. So they know that 99 has also been seen.
Yeah.
And then are they interested in trying to figure out what the reward signals were?
That's part of the posterior update, so they need to think about, given this is the recommendation, we'll see the example. Given this is the recommendation I got, what must have happened? I need to think about all the possible words where this must have happened, and that's why I can incentivize exploration, right? Because there are many words where this could be the recommendation. If the users observe everything, right, they will only take the posterior better action, right? So there's no way to guarantee exploration, because the posterior better action can converge to whatever. So there's no way to guarantee that I'll explore all options.
One more question there. Are you assuming the other people have been, is it an equilibrium or is it a dominant strategy? Like, does it depend on whether previous people have reported truthfully?
There's no reports.
No, sorry. I mean, whether they went with the recommendation of
Yeah.
the machine, or do you assume
Yeah, I
that
assume
people
that,
before you did?
I assume that it's a, yes. So I assume that it's an IC algorithm that everyone followed their IC, like.
It's kind of like following the recommendation is an equilibrium.
Yes. It's a, BIC, yeah.
Yeah.
Sure.
Sorry,
Sure.
this is good, but related to that, suppose that somebody in the past didn't, right? So I know it's incentive compatible, I don't care, right? I should do this, I'm going to do something different. What is actually reported? So here's the algorithm. What
It's not in the protocol, in fact, yeah. So, but you should think of it as they report the reward for the action that they took, and I observe that the action that they took.
Okay.
But at equilibrium, that's off the path in some sense.
Yeah,
I
it's
never
off
have it.
path, but that's a public
Yeah.
algorithm. Then.
So no, but that actually never enters in the sort of reasoning of like what would happen in that. But practically, that would be the system. So the information asymmetry is that the users do not observe rewards or recommendations of previous users. Right? So they're unaware whether rewards of previous steps have made a priori better arms seem worse than a priori worse arms. Right? So maybe restaurant A seems a priori good, but in the first 100 users, I've got like a lot of bad signals. And so given these 100 bad signals, now that restaurant is actually worse than the other arm. In that case, I should, if I was just exploiting, I would recommend the other arm. But they don't know whether I got like 100, bad signals.
Maybe you already said this, but I'm being slow. But is the incentive compatibility measured on individual actions or the whole stream? Because I could, like, if I've given you a lot of good recommendations, I can slip a bad one in there, and then still over time, you're better off listening to recommendations.
So you're only interacting once. Every agent interacts once with the system. That's the assumption.
Oh, okay. Because that opens the door for a little bit more.
Yeah, if you have multiple interactions with the same user, then that's a different mechanism design problem. And there's been some follow-up work that try to do that when you have playing with a discount of the player's utilities. But like here, think of it as either agents being myopic or interacting only once with the system. So is root regret achievable? And the main result of this line of work is that actually there's a black box reduction. Any bandit algorithm can be transformed into an incentive compatible one where the loss is only a constant, a constant blow up in the regret. So you can get root T based on incentive compatible algorithms. And in fact, it's a stronger reduction that T steps of any algorithm can be simulated in an incentive compatible manner in C times T steps, right? So you can simulate what would have happened without incentives, but you just need more time or more users. And so you can sort of simplify the design by designing what is your favorite, picking your favorite bandit algorithm, and also then picking, dealing with incentive constraints separately. What else I want to say? You get a lot of like the nice results from the bandit literature. You can get prior free or detail free type of algorithms that don't depend on the prior so much. So I don't need to know the prior very accurately. You get like these large gap results of log T regret. The other extensions that I wanted to mention in terms of preview of results, what happens when there is observed agent heterogeneity, that goes to what I said before. We can handle that, and the context could be changing the prior beliefs, and so then you can do contextual bandit algorithms, simulate them on top of the incentives. And then there is the unobserved heterogeneity, where the priors correlate with the reward in a manner that introduces what's known as unobserved confounding in the causal inference literature. And this is the new progress that we've made, where you can use recommendations as what's known as instruments in the causal inference literature and still incentivize exploration using instrumental variable techniques and estimate what is the correct choice. And then we've also looked at extensions where you have multiple agents interacting with you simultaneously. Think about routing games, where you have all of your ways, you have all of your agents driving on the same road. You send recommendations to all people, but the rewards of different agents interact. And so what recommendation I'm going to send to you is going to influence, like what other people believe about their losses. So now this is a sort of a Bayesian persuasion game with multiple receivers, and we have also, like work around, like implementing what's known as Bayes correlated equilibria in this setting. All right. Given that I don't have much time, I'm going to jump right into the main idea. So how do you simulate any bandit algorithm? So let's think about very special case, 2 actions where the rewards are deterministic. So when I pull an arm, I see its actual mean, so there's no stochasticity. So say the mean, the prior on mean mu1 is uniform 1/3 1. The prior on mean 2 is uniform 0 1. So these are the prior expectations. So everybody would go to arm 1. Arm 2 would seem inferior. So how do we incentivize players to play action 2? And here the realized reward is assumed to be the same as the actual mean reward. And the key idea is that you can hide exploration in a pool of exploitation. So what the planner can do is pull arm 1 once, right? So we play that, we get back the feedback, which is the actual reward. And then for the remainder of the, say, K steps, or sorry, L steps, for everyone except one unlikely person, I'm going to recommend the posterior better arm, right? So given the draw from mu1, now the posterior better arm is the, like mu1 or expected mu2, right? But there is a chance that the draw that I get, which is mu1, falls below 1/2, right? So there is a chance that after the first person, arm 1 is now the worst arm from the perspective of the planner. So there is a chance that all of these blue recommendations are actually arm 2, right? Because there is a probability that mu1 falls below 1/2. So now, what happens from the perspective of a user in this pool? When they see a recommendation, they don't know whether I'm a blue person and it's just that mu1 is below 1/2, or I am this red person, right? And I got the recommendation just for the sake of exploration. And when I do my posterior calculation, there's some probability that I am the guinea pig, and so this is the loss, like the negative part, right? Because in that sense, in that event, the signal is useless. Or with this remainder probability, I get a positive, reward by following the recommendation because mu1 is smaller, right, than mu2 0. That's the event. So this is some positive effect, and this is some negative effect. But as L goes to infinity, you can always pick some constant L where this is going to be smaller, and you're going to get a net positive gains, right? So that's the basic idea, right? So you can always hide any algorithm within a pool of exploitation. You can hide an exploration step.
So, and you don't want to do it too early because then it will be obvious that you're doing this way. So
you don't. If it's deterministic rewards and I observe like actual mu1, then it's fine, right? you just need one person, and then I have all of the information. If you have stochastic rewards, you need to wait so that the information that you've collected could flip with high probability, right? So, and that's sort of the key idea. Like if you have stochastic rewards, you're going to have some initial pool of collection where you're going to get some realized rewards. Now you have a strong enough signal of what the mean of the dominant arm is. When you have that, there is a high probability that that the posterior mean of that dominant arm fell below the non-dominant arm a priori, and so you can incentivize people within a large enough pool to follow any recommendation that you want.
I mean, in this case, presumably you'd have to have multiple guinea pigs because to estimate.
Yes, so you can do that many times. You have these. At every period you simulate. Sorry, it's right here. So at every, I have my favorite bandit algorithm. That's what I implement in this pool. Now I just use that feedback to update my bandit algorithm. I go to the next pool. I get this feedback to update my bandit algorithm. In the end, I need, however, how large the pool needs to be to incentivize exploration. That's the reward that I'm going to be getting. So
if you had, to Thomas's point, if you had users that were returning though,
yeah,
they're going to.
That's problematic for all of this. Yeah, and that's where the discount in the utility plays a role, because then maybe I can have a large enough pool so that the fact that they're going to influence something in the future is anyway. So that's the key idea. How much time do I have?
2 minutes.
2 minutes, okay.
Should I ask or go ahead?
I just want to, okay, so that was the key trick from that earlier work. I wanted to go to the unobserved heterogeneity and say a bit about our recent work on how to use techniques from causal inference. So here we're going to imagine, again, so say two actions, but we're going to imagine that agents have types, right? And these are private types that are not observed by the planner. And say for simplicity again that the types are binary, either 0 or 1. And the type is unobserved and affects the baseline reward. So if they say, this is what the reward that I'm going to get, irrespective of whether I choose action 0 or 1. So this is what happens when I don't take the treatment. And the type is going to affect my baseline reward. It's not going to affect the treatment effect. Right? So theta, you can think of it as the treatment effect. But it can affect the baseline reward. And the type also affects the prior bias on the treatment effect. Right? So, and for simplicity, assume that you have one type that believes the treatment effect is positive, and the other type believes the treatment effect is negative. But also, when you believe that your treatment effect is positive, that also has a different mean on the baseline reward. One motivation of thinking about these types of confounding problems with private types. So, for instance, one anecdotal story is when interacting with product groups, you try to create a recommender system, say, for salespeople, which customers to go after. Most salespeople have this misconception or belief that the customers that yield high revenue are the ones that I'm going to have the biggest impact, right? But it's mostly those are going to have big high revenue customers, and your interaction with them is going to do nothing. And those are low revenue customers. Maybe there you're going to have some impact. But this is exactly this type of thing here. This is the revenue that was going to be brought by a customer. Like say you're this is a high revenue sort of customer. This is the revenue that's going to come irrespective of whether they get treated or not. When a salesperson sees a high revenue customer, they think, so they have some prior bias that the effect is going to be larger. Right? So for the types of the high revenue types, you have a prior belief of a positive effect. So in the absence of any recommendation, you're going to see salespeople go after the high revenue folks. And then if you just ignore this confounding bias and you see what's the revenue from the people that were treated and people who were not treated, you're going to get a very big effect. But it's just the fact that stemming from this confounding bias that those were customers that were already going to be treated, right? That were already going to have a high reward whether they are treated or not. So these are the types of situations of confounding bias within a recommendation system that we want to get rid of. And so that's exactly the point here. So if you just calculate the means of people that of the samples that were treated and samples that were not, that shows control, then the effect that you're going to get is not theta, but theta plus this difference in the baseline rewards. And that could be heavily biased. Here, the big realization was that we don't really need an incentive compatible mechanism in this setting. We can, even if our mechanism is not incentive compatible, as long as our recommendation has an influence on the taken action, then we can view the recommendation as what's known as an instrument in the causal inference literature. So an instrument is any variable that affects the treatment that was taken or the action that was taken, but does not affect the outcome other than through influencing the treatment. And here, because the recommendation is just a randomized algorithm that doesn't observe the private type, right, you can view the recommendation signal as an instrument. Okay? And the only problem is that that instrument might actually be very weak. In the first period, no matter what recommendation I sent, it's not going to influence the action that you take. So yes, it's a valid instrument, but it's not a strong instrument. And the main idea is how can you use information asymmetry to build stronger and stronger instruments over time. Right? And so that's the key idea of this work, that you can use the same tricks of information asymmetry with these guinea pig constructions that I told you in the first slide, to actually construct stronger and stronger instruments that correlate more and more with a taken action. And then you can use instrumental variable techniques to estimate more and more accurately the effect of the action. Right? I'll stop there. I don't have time to. Yeah. All right. Thank you very much.
We have time for some questions.
I guess I'm curious, within a phase, suppose you're using some standard multi-arm bandit algorithm over there. Are you updating dynamically using that algorithm, and therefore, for example, if you're using UCB or something, you may be changing your recommendation to those who are not the guinea pig in the course of that phase?
No,
or
that's
you're
fixed
throughout.
That's
so
fixed.
you use the algorithm and you update it throughout that phase, but the recommendation is fixed for that whole phase, and it can only change in the next phase.
And it's easier to argue about Bayesian regret, that everybody else pulls the posterior better arm. And so the utility from that thing in expectation over the prior is larger than the algorithm. So you don't incur regret from the exploitation people. And that's why you can get like at least as much reward as the algorithm itself. But if you want to also do like ex post regret, you need to argue that the posterior better arm didn't ruin a lot, right? So you need to do like more like frequentist sort of guarantees. And that's an extra technicality in the first paper, yeah.
Some questions?
Yeah, so you hinted at the hey, here's a contextual bandit extension in the first part. And which is, that's how we can think about, say, personalized recommendations and so on. But there seems to be a gap between that and, say, the second part where it's kind of personal baseline. Suppose that it were a contextual bandit, but the context is not revealed to you, but kind of has to be inferred, right? So that it kind of seems like a blend of. Yeah,
it's harder to. Yeah, I don't know how to. We haven't really worked out, more interactive systems where I can actually elicit the context. If you don't elicit the context, then you're back to sort of like a confounding bias story, but with a more complicated thing where the treatment effect also depends on the type.
Exactly.
Yeah. And then it's not clear that you can even estimate. Those are not identifiable in some sense from the observed information that you have. It's like you can identify sort of average quantities, like you can maybe identify what's known as a local average treatment effect. That's like the Mutu mentioned, like Hido Imbens. So that's sort of like his contribution to what average quantities what average effect quantities that you can identify.
But suppose the same user, suppose the same user comes back and you can start to, like a collaborative filtering algorithm. Oh, maybe I can start to estimate some, some context associated with a particular user when I see them over and over again by generalizing. Is there any way to add what we're doing to that kind of setup? Anyway,
I'm not sure, because
So, I mean, you could almost estimate and then proportion of those kinds if you want to think about it. And from there you can go on. It's not completely obvious.
So yeah, you don't observe types, so you don't know even
Yeah,
like
exactly.
proportions
But you
of
know-
types.
No, but if you go on repeating,
But
and
if
then
you're
some
repeating
number
with
of people are
multiple users,
repeating, then you
multiple
might.
But even after interaction with you, I don't know what your type was, right? I
Yeah,
just know
yeah,
whether
but
you
you
follow.
will-
No. So there's a type, but you know, you can make up your own type space
exactly.
like we do
That's
in
what I mean.
collaborative filtering.
That's
Yeah.
what exactly I meant.
Right.
I have not thought about that one. Yeah, like doing like more low rank factors or something
Yeah,
like that.
exactly.
Yeah, interesting. Yeah, it's an interesting idea. Like similar to how we use instrumental variables, maybe you could do things like synthetic controls
Yeah.
within this context, and then that would be sort of like how you connect with collaborative filtering.